Okay. Sorry about that. Had to take care of babysitter for our kids tonight. All right, so let me not forget to run the tests here. Okay, so that's just testing the recursive calls, deep recursive calls don't blow the stack. So yeah.
I had kind of a question, but I just wanted to see if I could correct my thinking here.
Sure.
I know that Clojure does not do TCO because the JVM does not support it. But if I understand correctly, that's only because Clojure is compiling down the JVM bytecode. We're actually interpreting the Clojure language directly up with the map, right? It can do its own TCO in the interpreter.
Yeah, that's true. So the question about Clojure not doing TCO, and actually Clojure does do tail call optimization. It's just explicit tail call optimization. So Clojure has a special form called loop that has a recur form in it. So it is able to do tail call optimization basically, but you basically define it explicitly in the code. It doesn't do it automatically. So yeah, so Mal has automatic. Some of that, you're right. Some of that is related to the limitations of the JVM and just expediency in implementing it. And I think some of it is performance efficiency. But yeah, you're right. In Clojure, it's explicit TCO rather than just sort of automatic TCO. Okay. All right. So, like I said, in step 4, we had a real Lisp, but it was a bit inefficient. In step 5, we implemented tail call optimization, so we have a much more efficient Lisp that can do, basically arbitrary recursion, which allows us to do, most anything we need to do, even with this small kernel of a Lisp. There's a few other miscellaneous things that are part. Whoops, how did that get selected? All right. In step 6, there's sort of a grab bag of things that we add to sort of flesh out our Lisp. So the first, if you look up at most of them, they're not actually changes to the eval function itself. They're around that. So there's some new core functions that we added that are added. They're actually already in there. I skipped over them before. There's a new function called readString, which what that does is that just exposes the reader to our mal programs itself. So you can actually do a read of a string and get back a mal type. Slurp is just borrowing from Clojure. That basically reads a file into a string. And then there's a new data type with some functions for that, the atom data type. And one of the things I borrowed from Clojure is immutable by default. So the Clojure types, you can't change them. But what you can do is create an atom type, and that atom type you can update what type it's referring to, and that allows you to do. It's contained mutation, but it does give you the ability to do mutation in the context of an atom, at least the reference to the state, not the values themselves. And it turns out you can do what you need to do that way. It limits you a bit, but it reduces a lot of the errors that can happen in your code. That was kind of a sales pitch for Clojure. Okay, and then the more interesting things are things we're going to define directly in our top-level environment, not as core functions, but as actual mal features. So the first one is, the most interesting one is eval. So we're going to create basically a new top-level eval function. And what that does is that exposes the eval function, our own eval function, to be available to mal programs to call. And then we have this called earmuff variable with stars on either side called argv. This is environment parameter. So if we call our mal interpreter with arguments, it basically allows us to use mal as a scripting language. And then there's finally a load file. And load file is another function defined in terms of other mal components. And what that does is basically read in a file, read it, evaluate it, and return the result. And so this is part of what allows us to have a mal as a scripting language. Okay. So let me, before we get to this hands-on, let me, let's see here. I did that one. Okay. Yeah, we'll just get rid of that. Okay. This one I'm going to do, move over to Python. This name is a bit of a historical accident. It really should be something other than file, but a lot of the things are sort of related to being able to evaluate files. So that's what it ended up being called for now. So these things are going to be implemented basically in this area of the code, most of them. Oh, by the way, one of the things I mentioned about Python. Let me just do that now. So I'm going to convert this. I think this is just, yeah. So what I'm doing here is actually just catching up on a bug in my workshop files. So I do want for, there's an Atom-related function, the Atom type related function called swap, and it needs to be able to, it doesn't have access, it's at a different level than the TCO machinery, and so we still have to have a Clojure, the ability to call this function from that. So I'm sorry, this doesn't really matter, this is just me compensating for my forgetfulness. Okay. Return F. All right. All right. So down here, what we're going to do is where we define our REPL environment here. We're going to add some things to our REPL environment. So the first one we're going to add is eval. Next one we're going to add is argv, which is the arguments that the script was called with. And then we're actually going to, let's see, I think I have this saved somewhere. I'm going to cheat here. So there's too much to type. I'm going to define, like we define not, I'm going to define a load file function. And this function, what it will do is it takes a single argument, which is a file name, f, and then we'll go from the inside out, which is often something you end up doing with Lisps to figure out how they work, sort of from from the inside out. So we're going to call the slurp function on that file name to read that into a string. We're going to, we want to be able to write mal code that doesn't have to always be wrapped in a do. And so what we're doing here is basically just wrapping this file that we just read in an implicit do. And then we're going to call read string. This is where the read string is the core function that exposes the reader. So we're going to take that string, we're going to read string on it, perform read string on it, which will return an abstract syntax tree, a Clojure code basically in memory. And then we call our eval that we're going to define up here. And then finally, we're going to have another case. So normally we fall through here and just do a while loop for our REPL, our read eval print loop. But in the case where we have arguments, or we're calling this on the command line and we have additional arguments, what we're going to do is So if we have arguments, we're going to treat that first argument as another program to run. And so we're going to call a load file that we just created on that argument and evaluate it, basically. And then we'll exit. If we don't have any of our arguments, then we'll just run our normal read, eval, print interactive loop. So the things I didn't implement are eval and argv. And let me just see how we're doing on time. If I just need to press forward or not. It looks like I just need to press forward. So like I mentioned, eval, this symbol in our environment, that's going to map to a Python function, Python anonymous function, that takes some other abstract syntax tree, some other object. And what it's going to do, any guesses here? Yep. That's it. So we have an implicit environment that we're using because in there's not this type of Lisp that Mal is an implementation of doesn't directly expose environments to your program itself. You can't refer to environments in your Mal code. So we're implicitly referring to the top level environment for our eval. And then for argv, all we're going to do here is a list of the rest of the Python arguments that are called. All right. So let me just show you the core because I skipped over these before. So read string here, all it does is just expose the read stir function from a reader, and slurp is just opening the file and returning it as a string. So let's see here. Okay, printer, something went wrong. Oh, I know what's happening. Wrong version of Python. All right, so let's do a read string first. So this, again, just expose the reader machinery so that we can actually invoke it directly from our Mal program. And what that returned is not a string, but a list. And we have an eval function which takes any sort of Mal type and evaluates it. And so you can see here, it knows that we had a list, we evaluated it. Now we could have done this also like this, where we use our list function to create a list that contains +2 and 3 and then evaluate that. Same behavior there. Let's see here. Let me just a test file here. Actually, let me first use slurp to read that file into a string. So you can see here, let me, it's a little, okay, so this file contains, it defines a function inc4, which just adds 4 to a number. And then we call inc4 and print out the result. So if instead of slurping it in, I do load file. So we call, that file actually calls inc4 with 5, and so you can see here that we printed out the result 9. That file, the final thing that it returns is nil, so you can see the return value nil there of that file that we executed. And if we did this right, we should actually be able to do basically the equivalent of that from the command line. Whoops, isn't that right? Test. Whoops, I need to actually run my implementation of Mal here. Okay. So at step 6, what we've basically accomplished is we've taken our step 4 Lisp. We've added tail call optimization to make it an efficient programming language. And now we've added just some miscellaneous top-level functions to basically expose some of the machinery. And just by doing that, we now have a scripting language, mal scripting language. So this again, that's a mal program that we're running with our mal implementation. Okay, let's see here. Yep. So I'm just going to push on so that you can see self-hosting because I think that's just an interesting thing to see in itself. So I unfortunately ran out of time a bit, so we're not going to have much more hands-on. I mean, feel free to keep iterating on what you're iterating and listening in the background if you want, but I'm going to press on to some minor additions to step 6. Now, normally in the full process, these additions would happen in step A, but I've backported it, and I'll get to that. So. Step 6. No, I want 6. Right? No. It's actually. Yeah. Okay. Let's go back. I'm going to switch back to Ruby here. Let me just look at this here. So, oops. Yeah, so step 6 plus plus basically is I want to be able to show you self-hosting, so I'm skipping ahead to some of the things that would normally be in step A. But let me just, and since the tests know these things as step A, I'm going to copy it to step A. Okay, so here's our Ruby step 6. So here's the Ruby equivalence of what I showed you before. So here's the eval symbol in our REPL environment with a lambda around it that just calls the eval. Here's how we do the list, the arguments, getting the arguments. Load file is basically the same, just slight differences because it's Ruby. So now, so stepping back a bit, the mal code that you've seen so far has basically just been one-liners for the most part that I've typed in on the REPL or that very short program that I showed you that had a couple of things in it. So now what we're going to add to our step 6, or really step A, is a few more things to allow us to really run bigger programs, bigger mal programs. So let me actually show you a larger mal program first. So I'll just let you look at this for a second. So if you're realizing what this is, you might be feeling a little bit like this is from the movie Inception, where you're really not sure what level of reality you're on anymore. But so this is a mal program, and it happens to be a mal program that is an implementation of mal step 1. And so any of the implementation of mal can run this program. And so I think there's just to run the step 1 implementation of mal in mal. There's just a couple of additions that I need to do here. First one, actually I think there's just one for this, so read line. So this is the one place where you need a synchronous version of read line that we were working on before. Just the way it's designed, it assumes synchronous read line. So this is actually, I'm going to leverage Ruby's built-in readline functionality here. The argument to the readline is a prompt. I honestly don't remember what the true value to the Ruby readline is, but I think it's needed. And you know what? I think that's all I need. So I'm going to run, the step A, make sure that still works, and yeah, cool. So, right. So just again, because this is a bit confusing, I'm running Ruby. Ruby is running our current implementation of mal. we're using the scripting functionality we just implemented to load up the step 1 implementation of mal in mal. And so this prompt that you're seeing here is actually it's different than the other prompt. It's mal user because that prompt is coming from the mal implementation of mal, not from the Ruby implementation of mal. Now this is step 1, so all it does is syntax check and print that. I can verify that it's not just printing the string by adding some extra spaces because those are stripped out by step 1. Let me just add, there's only a few more things. So that's all we can do right now is step 1, but there's a few more things that I can do, just add to our Ruby implementation. There's not much that's needed. So actually, most of it's in core, it's new functions. So one thing that we need to expose is just a way of throwing exceptions. Okay. Another thing that later steps depend on, the later steps implemented in mal, that they depend on is they need to be able to test whether something is a symbol. Because in step 2, if you'll recall, the eval AST implementation needs to check to see if that thing it got is a symbol. And so we need to add that functionality to our Ruby implementation to be able to use that from step 2 of mal and mal. And so it's that. And there's a final function. This is the most interesting one. We need a way of exposing some other machinery to be able to actually, so in step 2, we have this apply, the ability to invoke, also known as apply in the Lisp setting. And so I actually need that functionality. It's not something I can sort of simulate. So I'm going to implement apply as a function, but it's gonna expose some of the functionality we've already implemented, basically. But all right, this is it's weird, but basically what apply does, apply takes a function and some more arguments. And what it does is it runs, you know what the best way to show this is? It's just, wrong number of arguments, 2 for 3 in, of course I did it wrong. Must be in the apply. Here, just a second here. I probably just got, yep. I missed a minus. Okay, apply plus. So what the apply function does is the first argument is a function, and then it takes arguments to run that function with. It's sort of a, stepping back a level and allowing you to leverage the apply machinery that's down in there. There's another form of apply which can do, apply always ends in a list. The last argument always has to be a list, but you can put arguments to your function before that list. So what it does is basically takes, so if I did that, I could do and you'll see that the list function was basically called with the middle arguments concatenated with the list of the arguments in the end. But the most common way that apply is used really is just, apply function and a list of things. Okay? Let's see. There's a couple more minor things. And this is almost aesthetic rather than necessary, but it does help us keep track of where we are. So this one's Ruby. Oops. That's right. I get that right? Yeah. Should be fine. Okay, and then when we start this up, we're gonna give a nice message here for the user. Gotta keep track here. Okay, so let's just run that. So now when we run our implementation, it gives us just a quick header that tells us that this is mal and what underlying implementation we used for it. Okay, and I think we should have everything. Yep, so there's step 2. And let me just show you step 2. So because we're skipping over steps 7, 8, 9, and most of A, there's a bunch of, I'm simulating a bunch of things that we would have added, but I'm defining them in terms of mal itself. These are super inefficient, but they do work. They are correct. Those are just some core functions that I don't have yet. So here's, as you can see, here's the reader, the read function in mal, implemented in mal. Here's the eval AST, so we check to see, is that AST thing that we got a symbol? If it is, we call environment get. And by the way, let's see, environment get is yet another utility routine that I had to define. It's pretty ugly, but you don't need to really care about that. And if it's a list, then we map across calling the eval for each of those elements. Here's eval. As you can see here, if it's an empty list, we just return it. If it's not an empty list, we're using let here to pull out, to capture the result of running eval AST into EL. I mean, hopefully you're seeing in your mind the code that we're writing in one of the other languages here, and it is fairly similar. We'll pull out the first element of that evaluated list. We'll get the arguments, which are the rest of them, and then we'll call that apply. That's why I needed the apply here. The apply that I implemented in Ruby is going to be invoked here, and we'll call apply the function and the arguments that we just evaluated. And so, oh, by the way, here, just so you can see this, the REPL environment that we define here is actually a list because we haven't implemented hash maps yet, that data type. So we actually have a list that just alternates the symbols and the functions. And when this is actually evaluated, we're looking up the plus, minus, star, and slash functions from the Ruby, at the bottom layer. These are being basically lifted up into this layer. So that was step 2. Let's just go straight to step 6. All right. Okay. So just let stew on that for a second. So what this is doing is using load file. This is the load file implemented here. Right here. As you can see, we define load file. Again, it's important to keep in mind, when I did this, oops, we're running Ruby. We're telling Ruby to run the Ruby implementation of mal. And then we gave it the program, the mal program that we want to run is itself a implementation of mal. And then we're using that to run yet another mal program.
Can you run step 6 file mal?
So you want me to do this, right?
Yeah.
Let me try 1 first. Yep. Okay, let me, oops, yeah. I can't remember if this works completely. I think it does. It's just one of the things that, because this is an interpreted program and there's no like just-in-time compilation that's optimizing all this, you have an exponential slowdown every time you add a layer here. And so I don't know if this will actually come back in time, but let me go over to the full. All right. So this is the C implementation of mal. It's compiled. Running the mal implementation of mal, which is running, again, the mal implementation of mal. A different, all the memory is separate, the objects are separate. And I'm using that to call this simple mal program. So there's a bit of inception going on here. But I think this is, when I did actually, for the first time, write a self-hosting interpreter. That was pretty cool, and I do encourage you to continue this process. Try and do this from scratch, because the point when you get to this point, it's mind-blowing. Even if you've seen it, when you have your own code that does this, it's a worthwhile experience, and I think you'll gain a lot of knowledge about Lisp just by doing this. And doing the whole process. And I mean, I apologize that there's a lot of information here, and I'm sure most people are going to have to catch up later. But anyways, let's see here. Okay, so let me see how much time we got. Yeah, that's fine. Okay, so I'm just going to go quick through some of the other steps of mal. We're not going to do any hands-on for this. I'm not really going to show that much code. But I just want to give you a taste for what these different steps do. And again, the guide that you should have on your cheat sheet, and I'll also be posting this all this workshop material online, so you can get access to it for sure. So step seven adds sort of this. It adds a concept of metaprogramming, and it's sort of the first step of being able to treat mal code as data and manipulate it as data. So actually, I will show some code here. Let me go back here to workshop. No, actually, I do want to be over here. Let's see. Let's use the make implementation of mal for this. This is a full implementation. Underneath, it's all GNU make. Just it's rather verbose, but it's real. So quote. What quote does is basically it's a way of getting something. It's a way of saying don't evaluate this. You're short-circuiting the evaluator. So one of the things I can do here is, oops, not that. Oops. So if I want to have a literal list, I can use the quote special form to tell the evaluator, don't evaluate this, just give it to me straight. Okay. Now the quote, that's pretty trivial. It's not all that interesting. So quasi-quote is really where the power lies. I'm going to define a couple of things here. And quasi-quote by default does the same behavior as quote, except that quasi-quote has some special forms that can be contained in there that have special behavior when you use quasi-quote. So I can have unquote here, not 7, X. And if any of you have used powerful string templating before, string templating basically allows you to have a string literal, but inside the string literal, there's some special symbols that say, I want to step out of the string templating, access some program data, and then insert that into the string. And that's kind of what's happening here. So quasi-quote, when it encounters the unquote X, what it does is it steps back and says, okay, I want to reactivate the evaluator just for this thing. and then insert it right here. And there's another special form, a special form that only can happen inside quasiquote, unquote, and splice, unquote. This won't be 9. And so splice unquote, if I just done unquote here, I would get y directly in that position. If I do splice unquote, it basically puts it into a list that's already there. So anyways, this is the beginning of sort of being able to do metaprogramming, where your program is manipulating programs. What's that?
Self-modifying code, in other words.
Yeah. This would be one of the tool set that you'd use for doing self-modifying code, but not just self-modifying code. The more common use of metaprogramming is that what we're going to get to next, which is macros. And so macros are a sort of what is probably what Lisp is often known for. You don't end up creating your own macros all that often in most circumstances, and if you do, you probably need to step back and ask yourself whether that's really the right approach. But macros are extremely powerful, and what macros allow you to do is basically you can write code with code. So rather than self-modifying code is one way of looking at it, but macros allow you to basically generate new code. And another way of looking at a macro is a way that as a mal programmer or a Lisp programmer, I can create new special forms. And the reason that's important, let me give you a concrete example here. Do I want to do any other implementation? I don't remember if I have all the dependencies. Nope. I'll just stick with make. Yeah, I do have awk. I didn't do that one, actually. So somebody else. Okay, here we go. All right, so I copied this, but this def macro is a special form that creates a function, but it's a special function. It's a function that's marked as a macro. And you can see the function. It has it uses quasiquote. And let me show you what happens. Macro expand is another special. What that does is it looks to see if what you're about to do is a macro, and it short circuits the final step of calling a macro. So I defined a macro called unless, and basically what it is it's flipping the if. It's a reversed if. Is basically all it is. And so if you look up here into the quasiquote, what you'll see is that we're doing an if unquote of the predicate, but then we've reversed the order of B and A. So again, this is using both quoting and macros. And so if I do, I'll get 7. But importantly here, unless is a macro that transforms the code that you give it, or the arguments, transforms the arguments that you give it somehow, and then calls eval on that. And so if you look up to the macro expand, what basically happened is that unless ran, switched the two arguments, and gave you an if. And then when you actually run unless, it does the macro expansion and does an evaluation step. And so it's a way of defining it. So the reason this is important, I was about to get to, is that if I tried to define unless as a function, a normal function, what would happen here is that it would evaluate true, evaluate pern 8, and evaluate pern 7. So you'd get 8 printed out, then 7 printed out, and then finally you'd get nil printed out because it's doing all the. Maybe a better way to show this would be. So this is one of the examples of where do is useful, where we want to have a side effect and return something. And so If unless was a normal function, we would have had 8 printed out. Even though 7 was returned finally by the function, by the unless function, we would have gotten, because we can't, in normal functions, we can't control, when we get the arguments, they're already evaluated as a normal function.
Lazy evaluation of arguments?
Yeah, I mean, lazy is one way of looking at it. I tend to think of it as macros decide how to evaluate arguments. So you could define macros so that they evaluate all their arguments first, and then, so you can make a macro that operates basically like a function, but you can choose to do whatever, you could evaluate these things in a different order. You could make a macro that changes do so that it evaluates them in the reverse order.
Yeah, so
right?
It's a big facility, it was something that would allow you to do lazy evaluation.
Yeah, exactly. And this, I'm not going to get a chance to show you some really interesting examples here, but basically, well, I can, so or, 7. Or is a macro that starts evaluating each of its arguments. And as soon as it comes to something that's truthy, it returns that. And it doesn't evaluate any more arguments. This is, again, something you couldn't do with a function, with an OR function. It would try and evaluate the 8. And then, it would evaluate all these arguments, including the 8. It would still return 7, but if the 8 position had a side effect, you would see that. So, also efficiency here. If 8 was rather a function call that ran for 15 minutes, most of the time you probably don't want to do that, and that's why you had the or there. So, okay. Let's see.
Does the def macro have to be built on top of both quasi-quote things, or are those just...
No, it doesn't. No, it doesn't. It doesn't at all. That's just, it's convenient. It makes defining macros a lot prettier, because otherwise you have a lot of like list. Like you're constructing this big list of stuff, and the ability to have the quoting and unquoting makes building macros a lot easier. If you're interested in macros, there's this is just touching on the bare surface, but there's many research papers and books and things that you can get into. So exception handling. This just adds a new special form called try-catch. And try-catch looks like, let's see here, let's copy something. Let's do this one. Oh, I haven't built it yet. The downside of when you have a compiled language. All right. So here's the try-catch special form. So what it does is it tries to evaluate its first argument. If that throws an exception, then it will catch that exception. The implementation of mal will catch that exception. It will bind that exception to the first argument of the catch block, and then it will evaluate the second argument of the catch block in that environment. So it creates a new environment for the catch block with the exception bound in it. And so you can, so here I tried to call ABC, which doesn't exist. That threw an exception, but this form as a whole didn't actually throw out an exception. It caught it, it evaluated the catch block, printed out the exception, and moved on. And then also in step 9 is a sort of a grab bag of other things, other useful core functions. And then the final step A is, we've already touched on a lot of the things that we added here because I short-circuited and added it to step 6, but there's a few other things here, including, by the way, back in step 9, I should say, this is a good place to add vectors and hash map support. If you haven't done it already in your mal implementation, that's one thing we haven't touched on at all, but it makes your code a lot prettier, and it's hash maps are a data structure that you definitely want. Step A, in addition to the things that we showed, one of the things that's added here in step A is metadata. The mal implementation of mal in mal that I showed you is much more verbose than it needs to be because it doesn't have some of these data types. It doesn't have metadata. So the actual in the full mal repository, if you look at the mal implementation, it's much shorter because it uses things like metadata and hash maps for the environment and that kind of thing. So it doesn't have to go through hoops to do that. So okay, I think that's basically yes.
So the approach you've outlined today, can you compare like what this can do versus like a monad transformer approach?
Monad transformer approach.
I understand that approach. I'm just curious if there's like things that aren't possible one way versus the other.
I don't know, actually. I'm a monad beginner, so I'm hoping to learn more about that in some of the sessions here. So unfortunately, I can't. I don't have anything useful to give input on that. I threw up some of the links again. Most of these are on the cheat sheet. I don't. Let's see. Yeah, I don't have a. Actually, I do have a link. There's nothing there right yet, but the LambdaConf, the GitHub Kanaka LambdaConf, that'll be where this material lands. Yeah.
Where's the slides?
That's what I mean. These slides that I've been presenting. It's the third link there. That's where it's going to be. They're not there yet. I haven't pushed them. I was modifying this all the way up till 2 hours or an hour before this. So I haven't pushed it there, but I will. That is where I'll push it. One thing, I don't remember I mentioned this or not. Oh no, I did mention it. There's the Slack channel. So if you want to be working on this during the conference or in the week or two afterwards, I'm going to be hanging out on that channel. I answer any questions that you have. Also, feel free to catch me during the conference and ask questions. Show me your broken code, and we'll look at it together. And then longer term, the hash mal channel on IRC for general discussion of mal. Some of the people who've created mal implementations hang out there, and you're welcome to join that and discuss. There's my Twitter handle, and I work for Viasat.com. And I think we have 2 more minutes, so we're just going to show some inspirational material. These are languages that don't have implementations in mal yet, of mal in them. So if any of those up here were languages that you're interested in learning and you really wanted to learn deeply, I have found that implementing mal in a new language is a way to learn that language really deeply. And to be honest, it's the most efficient way that I've personally found for learning a new language is to implement something real like this. And so some of these would be more challenging than others, for sure. A lot of the low-hanging fruit has already been implemented, but feel free to re-implement any language that's already been implemented. I won't guarantee that I'll pull it into the repository, but I would be happy to throw a link to alternate implementations if you have an implementation that's complete in an existing language. But yeah, so let's see. Do I have anything else? I think that's it. So I think that's the end of the time for me. Any other questions that people have? Here's just a kind of interesting. This is made a while ago, so I think about 10 implementations are not represented here. But this is a. If there's no other questions, I'll just talk about this. This is a graph that shows popularity, one measure, language popularity, not definitive, on the x-axis, going over to the right. And then on the y-axis, I have a few micro benchmarks that I run. And so it's probably pretty hard to read, but I can just tell you, down in the very lower left-hand corner is mal itself. And the size of the bubble is how many lines of code, the implementation. The colors represent the typing discipline, the fill color. There's lots of information here, but some of the most interesting language, in my opinion, are the ones that are in the upper left-hand quadrant, which have good performance but are not popular. So like RPython, Nim, Crystal, Kotlin, OCaml, Factor. This little bubble right here is Factor, which is an interesting language. It happens to be one of the smallest implementations. It also happens to be the fastest dynamically typed implementation. But it is a stack-based concatenative language. So if you're up for learning a new programming paradigm, if you've never touched that, it's an interesting language there. Also an implementation I didn't do. So Other questions before we break? Like I said, I'll be available and around and on the Slack channel. Try and answer as as quickly as I can, but I do have kids and they're here, so we'll see. We'll see how quickly I'm able to answer. But anybody who wants to weigh in and help out and catch me while I'm here at the conference, I'll be happy to answer any questions or discuss them out. So.